Hello, I'm Qihong Han from Beijing University of Information Science and Technology in China. I'm glad to share my paper with you here today. The title of my paper is Vulnerability Detection by Sequential Learning of Program Semantics via Graph Attention Networks. I will present this paper in four areas: introduction, approach, experiments, and conclusion. First, I will share introduction. As the open source software community continues to expand, the issue of software vulnerabilities has become increasingly prevalent. The total number of vulnerabilities recorded in the CVE database has grown from 4639 in 2010 to approximately 21085 in 2023. Vulnerability detection becomes more important. In recent years, an increasing number of researchers began to employ deep learning for vulnerability detection. Some workers began to adopt an automatic detection approach based on natural language processing. They analyzing source code as linear sequence and employ recurrent neural network for vulnerability detection. However, this natural language-based approach only utilizes partial information from the source code, posing significant limitations in understanding the complexity of vulnerabilities within actual source code. With the evolution of graph learning, some researchers have debugted source code using graph structures. They constructed a composite graph from AST, and DDG and employed graph neural networks for vulnerability detection. Using of composite graph present more structure and logical features of the source code, but their approach also have the following drawbacks: overlooking finer-grained control flow and complex data dependence relationships, failing to fully capture the precise structure and behavior of the origin code, assign lower significance to the semantics of code segments. To address their limitations, we propose a general and easily extensible framework: sequential graph attention networks for vulnerability detection. Second, I will share approach. The framework of our approach consists of three parts. The first part is code proprietary graph embedding layer. At this layer, source code functions are transformed into ST, SVG, and DDD graphs, and node embeddings are learned through the two-way model. We utilize breadth first search to generate sequences from AST, CFG, and DDG. Then there's different graph sequences were connected to construct three independent corpora. Finally, through training on their three corpora, three independent two-way models were obtained to learn node embeddings for corresponding graphs. In sequential learning layer, we constructed a sequential module to learn the feature information of AST, CFG, and DDD respectively. We chose GAT model to learn graph features in this study. It is because that GAT model is more suitable for directed graph learning due to its vertex-by-vertex operation mode. To avoid the problem of graph information loss when constructing the TPG graph, we built three GAT models for graph learning. The trained graph features are fed to the force prediction module for prediction. To fully exploit source code information from different perspectives, We propose the fault prediction module to merge their semantics features and perform graph-level prediction. The graph features learned from the sequential modules contain all the information from the original graphs, overcoming the drawback of losing subgraph feature information that may occur when folding. For the feature folding approach, we use vector concatenation. Finally, we need to perform a graph level prediction tag to prediction. Here we choose multi-layer perceptual for graph level prediction. In the SGVD, we design the graph features learned through the sequential learning module can serve as inputs for any prediction layer, whether it is a traditional machine learning prediction model or a natural network model. In order to verify the performance of SGVD, we have done a lot of experiments. The experiments in this paper were designed to answer four research questions. How does the SGVD framework perform compared to other vulnerability detection methods based on graph natural network learning? How is the extensibility of the SGVD framework? Third, why does the SGVD utilize the GAT model instead of the GN models adopted in division and regivate? Can SGVD learn features from individual code representation graphs, comparing with a single code property graph? Does our folding of multi-code proprietary graphs improve the accuracy of vulnerability detection? Our experimental setup is as follows. Our experiments utilize the dataset from division. It is a connection of original functions reassembled and labeled by the division team. Continue to large C language open source projects. SGVD is compared with the current best graph natural network-based vulnerability detection methods. Division and REGVD, we employ accuracy, precision, recall, and FE score as the evaluation metrics to measure SGVD's performance. How does the SGVD framework perform compared to other vulnerability detection methods? The results shown in Table 2 reveal that the SGVD framework significantly outperforms the baseline approaches. We noted that division exhibits a higher recall rate than our model, suggesting that the division model may have a higher false positive rate, resulting in more benign functions being erroneously predicted as vulnerable. To explore the scalability of the SGVD framework, we applied SGVD to 9 machine learning algorithms for performance testing. Results from Table 3 show that the performance of each base clear under the SGVD framework is significantly improved. While the SVM model had the best overall performance, with its average performance only 1% lower than the SGVD that utilized deep learning. Even the worst performing model, X-Trace, outperformed the baseline models. For comprehensive evolution of the activity framework, we averaged the result of 9 basic classifiers in Table 3 and drew the histogram shown in Figure 2. As shown in the figure demonstrated activity average demonstrated exceptional performance across all metrics, showing the stability and reliability of the SGVD framework. To answer RQ3, we conducted a series of abandoned experiments by replacing the GAT model with a GN model within the GAD framework, subsequently evaluating the impact on performance, as shown in the Table 4. Selecting the GAT model for growth learning within the activity framework is more effective than opting for GN model. In our research of Argue4, we evaluated activities' ability to learn from diverse individual code representations. According to the results in Table 5, our framework performance admirable when trained on individual code representation graph, with CFG demonstrating the highest performance among the three tables of code prepared graphs. Moreover, the detection performance improved significantly after fusing features from all three graphs, surpassing the performance achieved by any single graph. Our conclusion. This paper presents SGVD, a GAT-based framework for sequential vulnerability detection. SGVD extrudes semantic and semantic features from STCFG and DDG code property graphs, integrating them at the vector level. This enhances its ability to detect complex vulnerabilities. The combined features are fed into a multi-layer perception for prediction, effectively addressing the issue of missing feature information. We have done extensive experiments to demonstrate the performance of the activity framework, which outperforms existing graph learning vulnerability detection algorithm and show the scalability of the framework. Moving forward, we will explore more trivial vector fusion like low-rank fusion to improve our framework. We will also test activities' effectiveness in detecting vulnerabilities in other programming languages. Thank you all for listening. It's an honor to present at the IEEE SMC conference. I appreciate the organizing committee's efforts and the valuable feedback from everyone. I hope my presentation was helpful and I look forward to further discussions.